A very common course that many students undergo in an engineering program is a course on signals and systems. So there, in that course, you learn about what a signal is as a generalization of the notion of a function on one hand. And then you talk about the same signal in the sense of its transform domain. So you have the natural domain signal on one side and the transform domain signal on the other. And the most common transform that is used is the Fourier transform, where you think of a signal as a combination of sinusoids. Now, one big problem that people face is how can you first think of a signal for all time, for infinity, right from minus to plus infinity. And then again, how could you consider the entire frequency axis from minus to plus infinity? If you do it, you have to decouple the two domains, the time domain and the frequency domain, which is not a very natural thing to do. Look at the context of audio, for example. If I'm trying to describe music, I'm always going to think of it as some frequencies lasting for some time. So you have notes being played for a short interval or snippets of music which comprise of a combination of frequencies over a certain interval of time. So time and frequency are very closely interlinked. It is really difficult to separate them and take them as two separate domains. We are going to do this formally in this course. So how do you take the two domains together? And the same question actually can be addressed by a different perspective. That is, how do you look at a signal at different levels of resolution? So for example, if I'm looking at a scene from a window, I don't really see the scene as a set of picture elements or a set of intensities at different points, the way you would describe a function in two dimensions. What I see is first some broad features, and then I see some specific features at some coarse resolution, and then I go on refining my resolution until I see details. That's how we see and perceive. So we would like to capture this in our signal processing paradigm, and that is what we are trying to do in this course. Now we'll do it first in a discrete or a discretized domain, and we will slowly move into a continuous version of it. But in that journey, we would first need to understand a lot of concepts related to the movement from continuous time to discrete time, the challenges in it, a challenge called uncertainty that we encounter, and finally we would look seriously at what limitations we have to overcome and then do the best that we can to live within these limitations to do time and frequency together. So this in a nutshell is what we are trying to do in this course. And I will have a little discussion with my teaching associate who is right here with me, so that you can also understand as a student how you should go about taking this course and getting the best out of it. This course is entitled Fundamentals of Wavelets, Filter Banks, Time Frequency Analysis. Let me tell you in a nutshell what these three things are. So you have wavelets, which is a systematic way of looking at data and information at different levels of resolution. Filter banks, a way of dealing with this with discrete time or discrete natural domain, and of course transform domain too. And time frequency analysis, a more general perspective on the conflict between the two domains. How do we resolve it and how we can get the best in the challenges that we have. I would like to introduce to all of you my teaching associate, Shivam Bharadwaj, who is with me today. Shivam and many of his friends have helped me a great deal in creating this massive open online course, including all the supplementary material, exercises, demonstrations and so on. So Shivam would be the right person to tell you a few things about this course, and I'm going to ask him and he's going to talk to you now. So Shivam, first thing, who do you think will benefit from this course?
Okay. So students, working professionals and various teachers who are teaching in different engineering colleges can benefit from this course. Students who encounter data in their everyday engineering studies, People working in electrical engineering encounter data in the form of images, videos. Now, if we go to geophysical engineering, geophysicists encounter data which are from our upper Earth atmosphere, data from oceans. Now, let us consider the working professional. One of these field is time series analysis, econometrics, and data analysis. These fields have developed various advanced methods of analyzing these time series models, forecasts with the help of wavelets. All those professionals who are interested in doing data analysis can benefit from these courses. Teachers who are involved with the teaching of signals and systems, because wavelets not only is a tool for signal analysis, it has been proven to be a very important tool in the identification of systems. So not only the faculties or the teachers who are working in signal analysis are going to be benefited from the course, but faculty do some research in the field of systems engineering, for example in the field of ordinary differential equation, partial differential equation, are also going to get a great deal of benefit out of this course.
A few words of conclusion. What is most important is that you must see both the simplicity and the depth in this subject. You must enjoy doing this subject. Don't just take it as a whole host of formulas and derivations. It should be taken as a story right from the beginning to the end. Thank you.